Okay, so this is sort of going to be a little bit of an introduction to linear equations. This is actually the first video out of 3 that are kind of going to be all connected. I decided to break them up just to make it a little bit easier to sort of put things together. So far, from the Intro to Algebra video that you hopefully have already watched, we've been dealing with situations where we've had problems like this, where it said 2x plus 4 equals 12. And you may have seen this called on Khan Academy a two-step equation. The expression above is asking you to figure out what x is, or what went into this expression, in order to get 12. So there are really 3 things going on here. We've got an input, or x, right? That's what we're trying to figure out, what went into this. Then we have what's called a function. And by a function, we just simply meant some stuff happened to the input. In this specific example, it got multiplied by 2, and then 4 was added to that. Then the last part is the output, which is the solution. So some number goes in, this function happens, which I think of as like a machine, right? I almost think of like a printer. You know, this number goes in, and then some stuff bangs around in there, you get it doubled, and plus 4, and out comes your solution. We can use trial and error to solve for this. We could just kind of guess numbers until we get to it. But what we've been doing so far with two-step equations is designed to really help us with this, right? So this says, okay, well, if 2x plus 4 is 12, right? Okay, well, we know that 4 was added to this to get 12. So if we take 4 away from here, and we take 4 away from here, then this is still going to be true, right? If 2x is 8, then 2x plus 4 must equal 12. This is algebra. We're able to work with this without knowing what x is. And then we say, okay, what number when it gets multiplied by 2 is 8? Or effectively, we are dividing both sides by 2, right? If we divide this by 2, we're left with x, and 8 over 2 is the same thing as 4. And now we could go check our work, right? What is 2 times 4? Well, that's 8, okay? That's what it should have been. 2x should have been 8. And then when we add 4 to that, 8 plus 4, that's 12. Yeah, so, okay. The input to this function, in order to get an answer of 12, is 8. Now, we can use this same function, but figure out the input for other outputs, right? Instead of 2x plus 4 equaling 12, like we just did, what if it equaled 14? Well, that's a new problem, right? So we say, okay, well, let's subtract 4, and 2x is 10, and we know 2 times 5 is 10. So in this situation, x must be 5, right? I'll show that work up here. 2x plus 4 is 14. We subtract 4 from both sides, right? And we say, okay, that means that 2x must have equaled 10 if 2x plus 4 is 14. And what number times 2 is 10? Well, x, that's 5, right? And we could use a different solution. We could say, okay, well, what about when the output's 16? Same function, 2x plus 4, but a different output. And we say, okay, well, let's try that. 2x plus 4 equals 16. Hopefully, you've already figured this out, right? You should be able to do this in your head. You say, okay, I'm going to subtract 4 from each side, and that means that 2x is 12. And what number times 2 equals 12? Well, x must be 6. So what we're demonstrating here is that without changing the function, we can use different solutions to figure out different inputs. So now we can stick with our function 2x plus 4, but figure out what x is depending on different outputs. So using this same function, instead of writing like what is x if the output, I'm just going to make a table, right? And I'm going to give a list of different outputs, and I want to figure out what went into this function to get these different outputs. So we already said that, no, we did 12, right? We already said that if it's 12, then x must be 4. 2 times 4 is 8, plus 4 is 12. And we said that this had to have been 6, right? 2 times 6 is 12. I'm sorry, 5, excuse me. Got ahead of myself. So we said 2 times 5 is 10, plus 4 is 14. And then we said this one was 6. 2 times 6 is 12, right? And we notice a pattern, right? I'm going to guess this is 7. Let's try it. What's 2 times 7? That's 14. Plus 4, 14 plus 4 is 18. So yeah, this is 7. And using that same pattern, 7 to 6, 6 to 5, 5 to 4, I'm going to guess this is 3. Let's find out. What's 2 times 3? That's 6. Plus 4, hey, yeah. So we've now created a table. It's clear that the output depends on the input. with our function staying the same, the input determines what the output's going to be. When x is 3, then the output's 10. When x is 4, the output is 12. When x is 5, the output is 14. And in general, it's important to realize that there's this relationship between what goes in and what goes out. And that's what really linear algebra is all about studying, is the relationship between what goes in and what goes out. Now, one other thing, instead of writing when the output is x, right, I know that since this changes, it's a variable. And I'm already using the variable x here. So I'm just going to use the variable y, right? And I could use b or some other letter, but it just kind of makes sense to use y because y comes after x. So now in my table, I've got x here, right, what goes in. And then I'm going to set that equal to the solution, the output, y. So we can now use a table to solve x for any function, right? Here's a different function. So I'm asking you to figure out what must go into this function in order for the output to be 5. Equals 5. Well, I don't know. Let's figure it out, okay? So if negative 3x plus 2 is 5, then if I subtract 2 from both sides, I know that negative 3x must be 3, right? Because if negative 3x is 3, and then I add 2, that has to be 5. And now the same thing here, right? If I know that negative 3 times x is 3, then I say, okay, well, if I divide both sides by negative 3, that's going to undo this, and I'm going to be left with x. Well, what is 3 over negative 3? That's just negative 1. And we can go back and check our work, right? What is negative 1 times negative 3? Well, that's just going to be 3, right? And 3 plus 2 is 5, so yes. Now it says, what about when the solution is 2? So I'm going to use the same thing here. I'm going to say negative 3x plus 2 equals 2. And I'm going to subtract 2 from both sides, and I get negative 3x equals 0, right? Because I subtracted 2, and 2 minus 2 is 0. And now I know when I divide by negative 3, I'm still going to get 0, right? 0 divided by negative 3 is still 0. So when the output is 2, my input is 0. Okay, well, let's try another one. Negative 3x plus 2 equals negative 1. Okay. Well, I'm going to subtract 2, right? And I get negative 3x equals negative 1 minus 2 is negative 3. And when I divide both sides by negative 3, what is negative 3 divided by negative 3? Well, any number divided by itself is simply 1. And once again, I'm looking at this pattern, right? So I see that every time this is going down 3, that this is going up 1. Well, this goes down 3 again, so let's see if this is 2. I'm going to guess that this is 2. But we got to try it, right? What's negative 3 times 2? Well, let's see. Negative 3 times 2, that's going to be 6. I'm sorry, negative 6. Negative 3 times 2 is negative 6. Plus 2, negative 6 plus 2 is negative 4. Is that what we were trying to solve for? Yeah, okay. And then I can do the same thing. I can say, you know what? I bet this pattern is going to continue. In my table, I can see clearly that this went down 3 again. So let's see if this goes up 1. Let's see if that's 3. Oops, I changed colors. Let's see if that is 3. Well, negative 3 times 3 is negative 9. Plus 2 is going to be negative 7. Yep, that works. So I've now filled in this entire table of using this one function, negative 3x plus 2. I've figured out what all of these different inputs are for these given outputs. We can work backwards. Instead of saying, here's the output, figure out the input, we can say, okay, well, what if I put negative 2 into this function? What's the answer going to be? Well, 4 times negative 2 plus 3 equals, well, what is 4 times? That's negative 8. And negative 8 plus 3, get out your number line if you need to, is going to be negative 5. So that goes there. This is easy enough, right? What about when it's negative 1? Let's erase this. Instead of putting negative 2 into our machine, our function, let's put negative 1 in. Well, negative 1 times 4 is going to be negative 4 plus 3 is negative 1. And now we can put 0 into our machine, yeah? Let's see here. If we put 0 into our machine, what are we going to come up with? 4 times 0 is 0 plus 3. That means that this must be 3. And once again, I'm noticing a pattern, right? Every time that this goes up by 1, this is increasing by 1 each time. Every time my input goes up by 1, what's happening to my output? It's going up by 4, right? Negative 5 plus 4 is negative 1. Negative 1 plus 4 is 3. Negative 1 plus 4 is 3. So let's try this again. What's 3 plus 4? I'm going to guess this is 7. Let's find out. What is 4 times 1? Well, 4 times 1 is 4 plus 3. Hey, it is 7. And so that added 4. And I bet that this is going to be 4 higher than 7, right? Because this went up by 1 again, and this went up by 1 again, so this must be 11. 4 times 2 is 8 plus 3. 4 times 2 is 8 plus 3. Yeah, that's 11. Sorry for the terrible outlining there. So we have clearly just figured out all of the different outputs from this function given a specific input. And now let's put this back to life for a second, right? We've gotten off on a bunch of different numbers. The whole point of this is to allow us to work with problems even if we don't know all the parts. And this is life, right? You have to deal with problems all the time, even if you don't know every little detail about the problem. You make assumptions. You have to try and figure out, well, if they did this and he did this, then maybe this is going to happen. You start making these, you start deducing what is going to be the best solution to your problem based on things that you may not know yet. So let's say Jose decides to start up a lawn mowing business. Every yard he mows, he makes $10. And he also decides he's going to spend $18 a week on printing flyers. Okay? What we want to do is we want to figure out, what we want to do, where did I just go? We want to figure out if Jose makes $10 every yard and he spends $18 a week on printing flyers, how much money he's going to make. That's my output, right? How much money he's going to make each week based on the number of yards that he mows. Well, okay, let's think about this. If he doesn't mow any yards, he's not going to make any money, right? But it says he spends $18 a week no matter what on printing flyers. So he didn't make any money and he lost $18. So he's going to be at negative 18, right? Because he didn't make any money and he lost $18 printing up those flyers. But if he mowed 1 yard, then he made $10, right? So if he mowed 1 yard, he made $10 and still spent that 18. Well, what does that equal? 10 minus 18 means negative 8. So even though he made $10, he still wound up losing $8. 10 of that went to pay off this marketing, but there was $8 left. But what if he mows 2 yards? Well, if he mows 2 yards and he gets $10 for each yard, then that's $20. And he spent 18. So he winds up making a profit of $2. Yay, that's a profit. He made money. Well, what about 3 yards? If he mowed 3 yards, $10 for each yard, that's going to be 30 minus 18. And what does that come out to equal? Well, 30 minus 18, let's see, that's 12, right? 30 minus 18, $12. And lastly, if he mowed 4 yards, he made $40, still spent that same 18, right? So he winds up with 40 minus 18, which is $22. You can see this relationship of how many yards he mowed. The function was that he got $10 for every yard, right? The function is that he made $10 for every yard he mowed. And that he spent $18, right? So we can put in however many yards he mowed, and that's going to give us the amount of money he spent, or the amount of money he made, or lost in this situation, with his mowing business. Let's look at another problem. Let's say a cell phone company charges a base rate of $35 a month. They also charge 15 cents for every megabyte of data used. So we've got here, we want to figure out what's my bill going to be, how much am I going to have to pay, based on the amount of usage that I use on my cell phone. So we say, okay, let's say that I didn't use any data, right? Well, I still have this base rate of $35, right? So I used no data, but I did have to pay $35, right? So that means that I am going to wind up having to pay. So I'm drawing a subtraction sign. We have to add to that the $35 we owe. So $35 is the amount of money we owe. Now, let's say that we use 10 megabytes. Well, if we use 10 megabytes, right? If we use 10 megabytes and we get charged 15 cents for every megabyte, 0.15, then that's going to come out to $1.50. And then we still have to add to that the $35 that we owe, right? I really should line up my place values. We have to add to that the $35 we owe. And we wind up with $36.50 is what we're going to owe. We can keep going. Let me erase some of this. Let's say we use 20, right? If we have 20 megabytes of data used, and for each one we're having to pay 15 cents, right? Well, that's going to be double the $1.50 we paid, because this is double the data, so that's going to be $3. And we have to add to that the $35 that we're being charged no matter what, so we wind up spending $38. Well, what if we use 30 megabytes, right? That's going to come out to be 30 times 0.15, which equals $4.5, plus the $35. What does that come out to be? That comes out to be $39 and 50 cents. And then lastly, we say, what if we use 40 megabytes? So I say 40 times 0.15, 40 times 0.15, which comes out to be $6, plus the 35. Well, 6 plus 35, what does that come out to be? Yep, that comes out to be $41. So we've now used this table to try and figure out, cell phones actually do this. They charge you by how much data you use, plus like a flat rate that everyone gets charged. And so let's say that you and your family had decided that you couldn't spend more than $40 a month on your cell phone. Then you say, hey, okay, I really should not use more than 30 megabytes, because if I go over that, I'm spending more money than I have available to spend on my cell phone, right? So this is linear algebra at its finest, figuring out how much you're going to pay for your cell phone bill or how much money your business is going to make. We do these things. Our bill is our function, right? We had to pay 15 cents for every megabyte, right? So we knew that whatever the input was, however much megabyte usage we had, we were going to be charged 15 cents. And then we had to add to that the $35 that we were going to have to pay as a base rate. And that equaled the total amount of money we paid, right? We've used a linear equation to figure out how much money our cell phone bill will be. Let's look at one or two of the problems, and then we'll be done with this video. So this is kind of a special type of problem with distance and time, because you're going to see this on TCAP. There's a lot of questions about this on TCAP. So let's say we have a bicyclist that travels at an average rate of 3 miles every hour. We want to fill in this table. This is time, and this is distance. If they travel 3 miles an hour, well, if they don't put any time in, then they're not going to travel anything, right? That kind of makes sense. If you don't ride your bike, then you will have traveled 0 miles. If you traveled 1 hour, well, 3 miles per hour means that every 1 hour you travel 3 miles. So you will have traveled 3 miles. 2 hours, 3 miles for each of those hours. Well, that's going to come out to be 6, right? 3, we're just multiplying, right? This is 3x equals y. We've got our input, which is time, and our output, which is distance. And this is our speed. This is how much we travel each one of those hours. So we've got 9 here and 4. Well, 3, 6, 9, 12. So we're done. So here is a problem that I want you to do on your own and put it on your Google Doc. We say every day a store is open, it makes $25. So for each day that store is open, it's going to get $25. However, each month it has to pay a flat amount of $50 for the electric bill. So I want you to tell me, based on different scenarios for how many days the store's been open. How much is that store going to have to spend? How much money will they make or lose if they're open 0 days? If they're open 1 day, 2 days, 3 days, and 4 days? This is money, right? So good luck with that, and I'll see you at the next video.